All right, another guy, another circuit. So in this installment, I'm going to be studying so-called Hamiltonian circuits. These are similar to Eulerian circuits, but slightly different in that your goal is not to visit every single edge of the graph. Your goal is to visit every vertex of the graph. And you are only allowed to visit edges once, but the point is that you don't have to exhaust all the edges. So we're looking for a simple circuit, and it should exhaust all the vertices of the graph. That would be a Hamiltonian circuit. So let's take a look at a graph that did have an Eulerian circuit. Something like this. It has an Eulerian circuit because you can traverse the edges of this graph one by one without repeating any of the edges and visiting all of the edges and all of the vertices in that walk. But for a Hamiltonian circuit, you want it to be simple, so you don't want to repeat any vertices. And so if you try and do this, visit all the vertices, you're forced to repeat that middle one if you're to visit vertices on the left and vertices on the right. So it simply doesn't have a Hamiltonian circuit. And I want to just study a little bit about, what can we say if we know a graph does have a Hamiltonian circuit, and how can we rule out the possibility of having a Hamiltonian circuit. So it doesn't quite have to do with the degrees of vertices anymore. Maybe this example will convince you. Here's another graph that has a Hamiltonian circuit. Look. So I visited all the vertices and I haven't repeated any edges. And since I didn't have to cross this diagonal edge, the fact that I had odd degree vertices here didn't really prevent me from finding a Hamiltonian circuit. So unfortunately, we're not going to have this perfect characterization of which graphs have Hamiltonian circuits and which don't. But I can say the following. If I have a Hamiltonian circuit, then what the circuit is a little cycle walk through your graph. You start at one place and you cycle along all the vertices and come back to where you started. You never repeat a vertex and never repeat an edge. So what your circuit looks like is some sort of circular walk like this through the graph. There can be other edges in the graph. It's just that there is this walk that satisfies these four properties. So that would force the graph to have this subgraph that is connected, contains every single vertex, has the same number of edges as vertices, because a cycle is just a sequence of vertex, edge, vertex, edge, vertex, edge is the same number of vertices and edges. And the degree of each of the vertices in your little cycle is 2. That's what makes it a cycle. So if you find something like this, or pardon me, the other way around, if your graph has a Hamiltonian circuit, it must have a subgraph that looks like this. And that's what we're looking for when we're trying to find Hamiltonian circuits. So let's take a look at this graph here. Sometimes you just have to stare at it for a while and figure out if it's got a circuit or not. If this graph is going to have a Hamiltonian circuit, it's got to visit the vertex A, and since there are only 2 edges attached to A, they're going to have to be part of that Hamiltonian circuit, right? And same with L. L only has 2 edges. I got to visit L, so I'm going to have to use both of those edges. And let's see here. Can I conclude anything else about the other edges? I think J is the same. I'm going to have to include that one and that one. And so that's ruled out the possibility of using this edge here, right? D has to have this edge and this edge. And I'm almost done here. I just need to visit the other vertices. I think I can just complete it like this. So I found myself a cycle through the graph. I visited each of the vertices exactly once, and I haven't reused an edge. So this is a Hamiltonian circuit. And then let me show you in this example here how I can rule out the possibility of a Hamiltonian circuit. So I'm going to start with the same logic, and I'm going to say, since the Hamiltonian circuit would have to visit A, So I'm going to make the observation that the edges AB and AJ would have to be included in the circuit. And similar things could be said about C and G, and yeah, that's it. So I'm going to make observations about C and G now. Okay, and so since I know that these edges, these 6 edges, have to be included in any Hamiltonian circuit, I can rule out some other edges. Since this edge right here would force a visitation to D again, and I'm already visiting and here and exiting there, I can't have that edge in the Hamiltonian circuit. That's another way of saying that the circuit has to have degree 2. Each of the vertices have degree 2. So I can't have the edge DE in there, right? Let me be more emphatic about this and say must not be. Okay, and if the circuit is to visit E, which it has to, it must have these 2 edges. But now I've arrived at a contradiction because I've already got these 2 edges connected to B. I can't add a third. Okay, so there's an argument that this graph does not have a Hamiltonian circuit. So as I mentioned, we don't have like this really nice theorem that says a graph will have a Hamiltonian circuit if and only if it has some conditions, right? But there are some theorems of the form, if your graph G has some specific conditions, then it's guaranteed to have a Hamiltonian circuit. And I want to inspect one such theorem. This is a theorem by Dirac. Let me write it down here. And it states that if you have a certain degree condition on your graph, then you're guaranteed to have a Hamiltonian circuit. So it's like this. Okay, so if you know that your graph has at least 3 vertices and every single one of those vertices has degree at least n over 2, then you're guaranteed to have a Hamiltonian circuit. So what we're saying here is that if there are a sufficient amount of edges attached at each of the vertices in the graph, then you can build a Hamiltonian circuit. It's a really cool proof. It gives you a feel for how graph theory proofs go. If you like this section, you should definitely take a graph theory course. It's a really fun area. Okay, so the first thing I want to do to prove this thing, so let's suppose that we have a graph that satisfies these conditions. I want to first make the observation that G has to be a connected graph. That's somewhere to start. Why would G have to be connected? Well, otherwise, G would have more than one connected component, and if you look at the connected components individually, there's got to be one that has less than or equal to half the vertices, right? If you split G up into camps, then one of them's got to have less than or equal to half the vertices. So let's inspect that component, or like even the smallest connected component. And we're talking about simple graphs. I should have said that. So we're not allowing loops or parallel edges. And so if you're looking at a component of the graph that has at most n over 2 vertices, then every single vertex in that component can only be connected to the other vertices in that component, and there are strictly fewer than n over 2 many. This is a contradiction because every single vertex in this graph is supposed to have degree at least n over 2. Okay, so we know that G is connected. That's where we kind of start. Now is the key trick of the proof. What we're going to do is we're going to start in this connected graph with the longest path that we can find, any maximal path in the graph. And a path is a sequence of vertices and edges where no vertices are repeated and no edges are repeated. Okay, and I'm going to get some drawings going so that we can understand what's happening. So I'm not going to draw all of G. What I'm going to do is I'm just going to sort of elongate G in such a way that the path is apparent. So there are tons and tons and tons of paths in the graph G potentially. What we want to do is pick one that is as long as possible, right? So it has to be a path in that it doesn't repeat vertices or edges, and it needs to be as long as possible. Some paths are shorter than others. I mean maximal in that if I've arrived at VK, there are no other vertices that I can visit without either repeating one of the vertices back here, or traveling over an edge that I already have, which means that I would be, returning to a vertex that I've already visited. So that's what I mean by maximal path in G. Maybe one more observation before we keep writing. There are only n vertices in the entire graph, right? And perhaps this isn't all of them, but at most I have written down right here n vertices because that's how many vertices I have total. Okay, now because this path is maximal, all of the neighbors of V naught, that is all of the adjacent vertices to V naught, must be included in the path. So I'm going to use the term neighbors for adjacent vertices. So the neighbors of V naught are the vertices in the graph that are adjacent to V naught. That is the other vertices in the graph that have an edge connecting to V naught. Okay, why is that? Well, think about it for a second. If V naught was connected to another vertex that wasn't already in the path, we could elongate the path, right? Just by starting with that neighbor and then continuing on. And that would contradict the fact that this path was supposed to be maximal. So V naught's neighbors must all be included in this path that I'm considering. And as a reminder, there are at least n over 2 neighbors because the degree of every vertex in the graph is at least n over 2. And the same exact thing can be said about VK. I'm going to abbreviate neighbor as NBS because it gets annoying to write. Okay, so again, if V had a neighbor that wasn't included, I would be able to lengthen the path and that would contradict that it's maximal. Okay, now let me think about this for a second. So V naught has at least n over 2 neighbors represented somewhere in the path, and VK has n over 2 neighbors represented somewhere in the path. And let's just think about these numbers. So this visual might help. So there are at least n over 2 dots that the blue ones that represent the neighbors of V naught, and there are at least n over 2 red neighbors to the VK vertex. But as a reminder, there are at most n vertices in the line at all right? So in the middle here, there's like at most n minus 2 of those. So the blue and the red must sort of overlap each other. N over 2 plus n over 2 is n, all right? And there are only n minus 2 many dots in the middle here. So that's to say that the red dots extend down here somewhere, and the blue dots, like at worst, extend like this. So the claim that I'm about to make is understood from this visual. Like if you mark each of the dots with either blue or red, depending on if it's a neighbor of V naught or VK, you must at some point encounter a red next to a blue like that. It's because the n over 2 VK neighbors must reach down and the n over 2 V naught neighbors must reach up further. Okay, so let me actually get a new picture going to represent what I've claimed here. What I'm saying is that since V naught's neighbors extend more than halfway across from V1 to VK minus 1, and similarly VK's neighbors extend more than halfway across down from the V1 to VK minus 1, there must be an instance where VJ is a neighbor of VK, and the next one, VJ plus 1, is a neighbor of V naught, like this. So these are actual edges here that I've just drawn, whereas the rest of the path has these other vertices along it, like this. Okay, so here's the key, well, here's another key idea, I guess. If this is to be true, then look at this other path that I could make. So I'm going to start at V naught, and I'm going to like jump over to VJ minus 1, or pardon me, VJ plus 1, like this. And then I'm going to continue along the path up to VK. So I'll go VJ plus 2 all the way up until I get to VK. And then I'm going to jump back to VJ because they're adjacent. And then I'm going to get back to V naught, going backwards. So what I've made here is a cycle. Actually, it's not a path anymore. It's a cycle. Without the V naught at the very end, this is a cycle, a path. But this is just a nice, simple cycle, visiting each of these vertices exactly once and wrapping back around to V naught. But what's the point here? If there are any other vertices in the graph that are not listed amongst the V's, I'm going to get a contradiction. So let me think about this. If there are any other vertices out there in the graph, I know that since the graph is connected, I should be able to connect some member of the V's out to that member, right? So in particular, there is some neighbor of a member of the path that is not included in the list from V naught to VK. So there's one of two situations. Either all the V's are the entire set of vertices in the graph, in which case I've got myself a Hamiltonian cycle. If not, then there's some other vertex out there in the graph forcing one of the members of the path to have a neighbor that is not in the path, as I've drawn here. So I'm going to call this member of the path VI, okay, and maybe I'll call this one W. But this is going to be a contradiction, and I'll show you why. Take a look at this path. I'm going to start at W. I'm going to go to VI, their neighbors. I'm going to go down to V naught. And then I'm going to hop over to VJ plus 1. And then I'm going to continue on over to VK. I'm going to hop back to VJ. And then I'm going to continue back down to VI. I'll stop short of VI itself and just go to VI plus 1. Then take a look at this path that I've created. The visual helps me, see what it's doing. You start at W, you visit VI, you visit all the V's until you get to V naught. Then you wrap around and go to VJ. You visit all the V's up until VK. Wrap around, visit all the V's that are in between here. And you just stop short of visiting VI again. And what have you built? You have built a path that includes every single V, right? All of them are hit. And it's got W. So this path is a perfectly good path, but it's longer than the maximal path that I started with, right? So this contradicts the original path being as long as possible. Longest length, I think, sounds awkward, but you get the idea. Okay, so there's the proof.